Hello and welcome back. So let us continue with section 2.1. Last time we defined what is a line integral. But before we continue, actually, let me revisit the definition. Okay, this was our definition. Okay, if gamma is piecewise smooth, then the integral over gamma is the sum of Riemann integrals over small parts. Okay, now I want to attract your attention to the fact that we rarely use this definition as it is, actually. We use it in a particular case. So in particular, if gamma is smooth or just C1, then there is a very simple formula for the integral. It's just the integral from alpha to beta of f of gamma t times gamma prime. So this is a particular case of the definition. Okay. So this is the first formula. This is what we usually do. Now, we use this result together with a particular case of proposition 2.3, okay, which tells me that if gamma is a composition of paths and each path is C1, then the integral over gamma is the sum of the integrals. And now we compute each integral here by formula 1. This is what we use, what we do in practice, okay? So we decompose gamma into parts, each of which being C1, right? Okay, the two things are, okay, these are equivalent actually, but this is what you do in practice, okay? So now let us continue with our study of line integrals. If f is a function from an open set omega into C, an antiderivative of f is a holomorphic function whose derivative is the function small f. Okay, you know this, I think, but we have to assume that the function is holomorphic in order to talk about its derivative. Okay. Now, why are we interested in derivatives? For a very simple reason, actually, because if you have a derivative, it's very easy to compute line integrals. But unfortunately, not all functions possess an antiderivative, even holomorphic ones. So actually, we need two conditions for, we shall see later, that we need two conditions for the existence of an antiderivative. We need a condition on f, we need f to be holomorphic. We'll see why. And second thing, we need a topological condition on the domain omega. Okay? And I will give you now an example of a holomorphic function with no derivative. Okay? If you like the language of differential forms, saying that f has an antiderivative means that the differential form f of z dz is exact. Okay? Same thing. So the first result is that if you have an antiderivative, then it's very, very easy to compute line integrals without going back to the definition. Now, this is known as Barrow's rule. Now, not all mathematicians agree about the name of this rule. It states that if a function small f has an antiderivative capital F, then the integral along any piecewise smooth path is just the difference of the antiderivatives between the endpoints, right? And we write this, if you like, f of gamma t between a and b. Now, this formula looks very familiar, actually, because this is just a consequence of the fundamental theorem of calculus that you use to compute integrals, okay? Now, I took the name of this rule from Dr. Hello, who took it from his professor, actually. I think they did some research, and it seems that this rule was known, and the fundamental theorem of calculus was known to Barrow, who was Newton's professor. Okay? So it's very easy. Why? Okay, let us, as usual, start with the easy case. Suppose that gamma is just smooth. What happens? Then I write the integral of f as the integral of f prime, because capital F is a derivative, is an antiderivative. And I just apply the definition or a consequence of the definition, okay? Because I'm assuming that gamma is, so I don't need to decompose here. Now, if you look at the function inside the integral, you will notice something. It's f prime of gamma t times gamma prime. And what's that? By the chain rule, it's the derivative of the composition of f and gamma, right? And now this is just a Riemann integral of a derivative, actually. So the fundamental theorem of calculus that you know tells me that this is just f of gamma evaluated between alpha and beta. So it's f of gamma of beta minus f of gamma of alpha by the fundamental theorem of calculus. Okay. Now, if gamma, more generally, if gamma is piecewise smooth, then we do the decomposition. So we write the integral actually as the sum of integrals over small parts of the segment alpha beta. Okay, and now I apply the same thing here, but to the integral tk plus 1 rather than alpha beta. So I get the same thing. I get by the chain rule a total derivative, and this is just each integral is actually the difference of f of gamma between the endpoints tk plus 1. And now if you do that, you will see simplification. So for example, you get f of gamma t1 minus f of gamma t0, which is alpha. Second term, f of gamma t2 minus f of gamma t1. So the gamma t1 cancel, and so on and so on and so on. So there are simplifications actually that occurs, and we are left with what? We are just left with f of tn gamma tn minus f of gamma t0, which is just f of gamma beta minus f of gamma alpha. Okay, so it's very easy. So this is one reason we love antiderivatives. Okay, and I will illustrate the usefulness of this result on an example. So I will give you a horrible curve that I can draw actually, and I want you to compute the integral over this complicated curve of z2 dz. Okay, fine. If you want to go back to the definition, of course here gamma is C1, everything is C infinity here. Then you just plug in and you get gamma t squared times gamma prime. So you get this horrible integral. Now, this horrible integral is computable actually. If you, with enough patience, you should be able to do it. But no sane person would do it actually. So actually, and the curve looks something like this actually. It's a spiral asteroid. Now, not exactly, but something similar, because actually to draw this figure, I divided t by 2 here in order to, because otherwise it's not really clear. So it starts from this point, 1, 0. Okay, and then the final point is e2 pi, right? So these two are on the same line. Okay, if I didn't have the ET, I would have got the asteroid, which is closed actually, right? Now, how to compute this integral? Well, does Z2 have an antiderivative? Yes, sure, Z3 over 3. So I just apply Barrow's rule, and I get Z cube over 3 evaluated between 1 and E2 pi, right? And I get this result, 1/3 E6 pi minus 1, or 1/3 E6 pi minus 1/3, right? So you see that it's very, very easy to compute integrals, complicated integrals, when we have an antiderivative. But once again, not all functions possess an antiderivative, and I will give you examples later. Okay. The main theorem of this video now is Theorem 2.2. It established equivalences between 3 or 4 conditions. So, as usual, we have an open set, but I have to assume it to be connected, because otherwise we would have problems actually. So I assume that omega is open and connected, and therefore its path connected. So there really exist paths and loops inside omega. Okay. Now, if omega is not connected, I can work on each connected component, right? But to simplify the whole discussion, we assume it to be open and connected. Okay, so there is equivalence between three conditions. F has an antiderivative, which is a condition. Okay, not all functions, not all continuous functions, or even holomorphic functions possess an antiderivative. Okay, so it's a condition. This condition is equivalent to another one, which states that the integral over any piecewise smooth loop of f is 0, right? And the third condition is that the integral of f along any polygonal loop is 0. Now, what is a polygonal loop? A polygonal path is just a broken line. Okay, so it's just a path such that the path is linear, is a straight line segment on each piece, right? Each piece is a straight line segment. Okay? So it's just a juxtaposition of straight line segments. Okay, now I'll draw a figure. Okay, so these three conditions are equivalent. And if moreover omega is convex, so this is the geometric condition of omega, then there is an equivalence between f has an antiderivative and the integral over any triangle loop is 0. Okay? Okay, so we will prove that first 1 implies 2, 2 implies 3, 3 implies 1, and later we assume that omega is convex and we prove that 1 implies 4, 4 implies 1. Okay. So let us start with the implication 1 implies 2. So my assumption states that small f has an antiderivative, capital F, right? So if gamma is a piecewise smooth loop, then by Barrow's rule, the integral over gamma of f is just the difference between the antiderivative at gamma 1 and the antiderivative at gamma of 0, right? Or if you like, between alpha and beta, doesn't matter. But since gamma is a loop, so it means that the closed path, so the final point and the initial point coincide. So gamma of 1 equal gamma of 0, and therefore the difference is 0. Okay? So 1 implies 2. 2 implies 3 is trivial actually, because a polygonal path, a polygonal loop is just a piecewise smooth loop, right? So it's a particular case, right? Now 3 implies 1 is very interesting. Okay, so fix the point A in omega, and let Z vary in omega. Okay, so we have a picture like this. So A is fixed during this discussion, and Z is an arbitrary point. Also, it will be fixed actually, but it's my variable Z. Okay. Now, let gamma be a polygonal path joining A to Z, as in the picture. Okay, so this is what we mean by polygonal path. It's a succession of straight line segments. So I claim the following: if gamma and mu are two polygonal paths joining A to Z, I claim that the integral of f along gamma is the same as the integral of f along mu. So otherwise stated, the integral is path independent, right? It's not always true, but it's true here because I'm assuming that the integral over a polygonal loop is 0. Now, how to obtain a polygonal loop? It's easy. Now, but you have to pay attention to the orientation, actually. The orientation gamma is like this. So both gamma are pointing to the same direction. But we obtain a loop by composing gamma not with mu, but with mu minus, which is the opposite path of mu. So this is a loop now. Okay, what we see now is a loop joining A to Z and Z to A, right? So my assumption states that gamma star mu minus is a polygonal loop, right? So the integral over the loop is 0, because this is my assumption. This is 3. This is what I assumed. Now, I can decompose this by proposition 2.3. The integral over this loop, gamma star minus, is the integral over gamma plus the integral over gamma minus. This is proposition 2.3. But proposition 2.4 tells me that the integral over the opposite path is minus, or the negative, of the integral over the direct path. Okay? Now, since this is 0, the difference here is 0, and therefore these two quantities are equal. So we really proved that the integral of f is path independent. It just depends on the two endpoints. But a is fixed, that is variable, right? So this claim, actually, this result permits me to define the integral over any path, the integral over any polygonal path joining a to z. The integral is the same. So just pick any polygonal path you like, joining a to z, and integrate f along this. Then you get a function that depends only on z and on a, of course, but a is fixed during this discussion. So I really, when z varies, I really get a function of z, of the endpoint of the path, okay, by my claim. Because if you choose another path, you get the same result. So it's a function now. And now I will prove that this function, capital F, is holomorphic and its derivative is small f. Okay? So once again, okay, this is what I want to prove. So fix a point, fix z in the discussion now. Okay? Since omega is open and z is an omega, there is a whole ball of sand around a disk of center z contained in omega. Okay, here I took the biggest such disk, but it's not really important. So, okay, so here's the situation. I have a fixed point A here and another fixed point Z in this discussion, okay? And I choose a polygonal path gamma Z joining A to Z, okay? And it exists actually. I didn't say that, but this is true because omega is open and connected, and therefore it's path connected. This is why I assume that omega is connected in the beginning, right? Because if it's connected and open, it's path connected. So paths exist. Otherwise, the whole discussion is empty, right? So, and we proved that it's independent of this. So, okay. So choose a polygonal path joining A to Z. And in the disk of center Z and radius R, choose a point Z plus H, right? Where H in modulus is less than R, small enough. So H actually, so Z plus H is the point in this disk. So it's still in omega. This is why I need actually omega to be open, by the way. Because when I write the ratio fz plus h minus f of z, I need f of z plus h to be defined. So z plus h, so h should be small, right? And now take the path, just compose the path gamma z with the straight line segment joining z to z plus h. Z plus h is in red here, okay? And then this is just a polygonal path joining a to z, okay? Right? So by proposition 2.3, the integral of small f over gamma z plus h is the sum of the two integrals. The integral over gamma z plus the integral over this straight line segment joining z to z plus h with the same orientation. Okay, right? And now let us evaluate this difference, capital F of z plus h, which is well defined now, minus f of z, capital F of z, minus h, small f of z. I want to show what? I want to show that this quantity is a small o of h. So it's less than epsilon times modulus of h, right? In modulus. So the first term is by definition the integral over gamma z plus h, right? Of f. The second one by definition is the integral over gamma z. And the third term I didn't change. Okay. Now, what is the difference among these two integrals? The difference between gamma z over the integral over gamma z plus h minus the integral over gamma is this, the integral over this straight line segment, right? So So this difference actually is now the integral over the straight line segment joining z to z plus h of small f minus h f of z. Now let me write this difference as one integral. Now here, note that this is a constant. It doesn't depend on u. So I can write this as the integral from 0 to 1 of h of z du, right? And now, how can I compute that? It's very easy. There is a straightforward parameterization of this straight line segment joining z to z plus h, and it's given by gamma t equal, or delta t if you like, equal z plus th. So z plus th is actually what? Is the parameterization of this path. When t equals 0, we are at z, and when t equals 1, we are at z plus h, right? So by definition, this integral times the derivative. So it's f of gamma t times gamma prime, but the derivative of gamma prime is h, because z is fixed in this discussion. Okay? And the second one I didn't touch. So I put everything inside one integral, and I put the h outside. Right? So this is a typical procedure in analysis. When you want to prove that a quantity is small, we write it as an integral, and we prove that the integral is small, right? Now I already have the h here, so I want to prove that this integral, actually, when h is small enough, is less than epsilon. This is what I have to prove, right? So I take the absolute value, the modulus. When I take the modulus of this, I get the modulus of h times the modulus of the integral, but the modulus of the integral is less than the integral of the modulus. Sorry, this is f here. It's an error. It's f of z plus th, right? And this is something that you proved in principle in second year. Okay, so the modulus of the integral is less than the integral of the modulus, which, by the way, is not totally straightforward. Okay, unlike the real integrals of real functions, it takes a little bit of work to prove that. Okay, now I want to prove that this integral is less than epsilon if h is less than a certain quantity, right? But this is easy because this is a consequence of the continuity of f at the point z, which is fixed in this discussion. Okay, so what does it mean to say that f is continuous at z? It means that f of z plus k minus f of z can be made arbitrarily small provided k, the difference between z plus k and k, is less than a certain quantity, alpha, right? So now, in particular, if h is less, and modulus is less than this alpha, which depends on epsilon actually, then for every t between 0 and 1, the modulus of th is less than the modulus of h, so it's less than alpha, because modulus of t is less or equal than 1. Therefore, when I replace k by th, I get what? I get f of z plus th minus f of z is less than epsilon for every t in 0, 1, provided h is less than alpha in modulus. And therefore, we know that we can integrate inequalities. This is true for every t. I just integrate. And I get the integral of epsilon from 0 to 1, which is just epsilon. Right? And that's it. I proved that my integral is less than epsilon if h is small enough. And I already have an h outside in modulus. So I proved what? I proved that this difference is a small o of h. And this precisely means that capital F is holomorphic and it's at z, and its derivative is small f. If you like, you can divide by h and let h tend to 0, same thing. Okay, but we did these kind of things at the beginning. Okay, so this estimate actually proves that f is holomorphic and its derivative is given by small f of z. Okay, and that's it. So so since z was arbitrary actually in omega, capital F is which was defined by an integral, is an antiderivative of small f. So we completed the first loop. 1 implies 2, 2 implies 3, 3 implies 1. Okay, now suppose in addition that omega is convex. Okay, now 3 or 1 implies 4y because a triangular path or triangular loop is just a polygonal loop. It's a particular case. right? So 3 implies 4 always, actually. Now 4 implies 1. Once again, fix A and Z, and fix A and let Z vary. So as a function of Z, we can integrate f along the straight line segment joining A to Z. Okay, why? Why this is well defined? Because since omega is convex and A and Z are in omega, the straight line segment joining A to Z is entirely in omega. This was not the case if omega is not convex, right? So if omega is not convex, I cannot say that the integral of that the straight line segment joining A to Z is in omega, right? Because the path should be all in the domain over f is defined. Okay, so now it's easy. It's easier actually. So instead of integrating along a polygonal path joining A to Z, I integrate just along the straight line segment joining A to Z, right? So it's well defined. And now take H small enough so that it's inside omega. Okay, because if H is large, actually that plus H could be outside omega and capital and small f is not defined. This is why I need H small. Okay. So now consider the triangle AZ, Z plus HA. Okay, choose in this figure the orientation AZ, Z plus HA, but it doesn't really matter. But here it's counterclockwise in this figure, but it's not really important. Okay. Now my assumption states what? My assumption states, so assumption 4, it states that the integral over any triangular loop is 0. So in particular, the integral over the triangle AZ, Z plus HA is 0 in this direction. But I can split this integral into 3 parts, as we know from proposition 2.3. The integral over this triangle is the sum of 3 integrals. The integral over the straight line segment AZ plus the integral over ZZ plus H plus the integral over Z plus HA. Okay, so here pay attention to the orientation. Okay, so when I say that the straight line segment AZ, there is an orientation here. So this means that so now the sum of these 3 integrals is 0, right? So the sum of the first 2 here are the negative of the third one. But when I put minus here, I get the integral from A to Z plus H. Okay? Because this guy now is the opposite of this, which is equal to the sum of these 2. Okay? Or if you like, this integral from A to Z plus H minus the integral from A to Z is equal to this third integral from Z to Z plus H. And therefore, I can proceed as in the implication 3 implies 1. I just take the difference. So now capital G Z plus H minus capital of G is the difference of these 2 integrals, which is just the integral over Z plus H. And we can also subtract here minus H f of Z and repeat the same procedure, right? So we can repeat, if you forgot, you can go back. So the same thing, but instead of f, I have G here, and I have the same estimate, right? So, and I can continue exactly, I use the continuity of f, and that's so the same proof works. Okay, and that's it. Now the loop is completed. Okay, so 1, 2, 3, 4 are equivalent if omega is convex. Okay. Now, as a consequence, actually it's just a consequence of 1 implies 2. The function 1 over z defined on C star has no antiderivative on the whole C star. Okay, and this could be surprising. Okay, how do I know that? Well, let us compute the integral of 1 over z over the unit circle, whose parameterization is given by cosine t plus I sine t. So gamma prime is I e I t. So when I apply directly, I can compute directly by going back to the definition. So I replace z by gamma t and I multiply by the derivative. And then I simplify and I get 2 pi I. And this is something different from 0. If 1 over z has an antiderivative, then by Barrow's rule or the previous theorem, this should be 0. Right? So this is something important. 1 over z has no antiderivative on the whole of c star. Now, you may tell me, well, what about the logarithm? There's a problem in the logarithm. The logarithm that you probably defined last year, if you noticed, was not holomorphic on C star. You had to remove a semi-line, a half line from, so you had to remove maybe the negative x-axis in order to obtain the logarithm, right? So the logarithm that you defined actually is not holomorphic on C star. It's holomorphic on C without R minus, right? And now I will just end with I want to do this simple exercise to test your understanding. Show that the function z bar also has no antiderivative on C. Okay. Later, we shall see another reason why. Now, try to work with integrals, but there's another reason why z bar has no antiderivative. Okay. So this concludes today's video. Next time, there are 2 points that I would like to talk about. And then we'll continue with Gursa-Cauchy. Okay, next week. Okay, thank you for your attention and see you later.